AI explores physics and chemistry frontiers to win Nobel Prize. Such is the grandeur of this latest chapter in human history. At the Artificial Intelligence and Machine Learning activity of International Nathiagali Summer College, research community leading the current AI revolution gets together to discuss emerging trends and disciplines within the most cutting-edge AI technology. The previous AI activities at INSC have been graced by leading figures from industry and academia, hailing from the University of California, Berkeley, Cardiff University, University of South Wales, University Polytechnique Hosty, France, New York University, University of Cyprus, University of Kaiserslautern, Johannes Kepler University, Shenzhen University, University of Pittsburgh, Qatar Environment and Energy Research Institute, Hamad bin Khalifa University, ATRI in South Korea, Istanbul Medical University, and University of West of Scotland. Keeping up with the tradition, this year's AI and ML activity at INSC 50 will cover state-of-the-art AI research such as generative AI, agentic AI, Industry 5.0, AI augmented cybersecurity, neuromorphic computing, artificial general intelligence, and ethical AI. Our esteemed faculty this year hails from world's top institutions involved in pioneering work in various areas of artificial intelligence. Dr. Mohammad Shafique, Dr. Kun Zhang, Dr. Adil Razi, Dr. Bernard Jensen, Dr. Professor Shafayat, Dr. Grace Lee Zhang, Dr. Umarana, Dr. Valentina Amelia Blas, Dr. Shoaib Ahmad Khan, Dr. Suhail Zaberi are some of the top names in the industry who are from whom we are going to have a lot of benefit through their lectures. May God bless them all, and may we have a wonderful session. Ladies and gentlemen, everything has its goods and bads. Whenever there is a new innovation, whenever a new thing is created in this world, you can have something positive associated with it. It can be used for the positivity of the humanity, or it can be used against the humanity. For example, there was dynamite. It has caused lots of destruction in this world. And at the same time, the person, Alfred Nobel, who created this dynamite, he knew what he was doing. So he created basically the Nobel Prize so that peaceful means of science and technology can benefit humanity rather than destroying it. Today, we stand here where AI is basically the talk of the day. The same AI can also be used in systems like Lavender, Hapsora Gospel, and Where is Daddy and Pegasus to commit genocide against the Gazans by the Israeli forces. So we must not use AI for the destruction of humanity, for causing genocide. We are the ones, we get together to use AI for the positivity, for the development of this humanity. That's the main theme of this activity and why we are here, so that AI can be used to elevate the basic level of every human on this planet. Thank you very much. I'm very grateful for all of you for being here, especially our esteemed faculty members. And with that, I would like to start the first session. I don't know whether I should say anything or not. Dr. Mohammad Shafique, he's part of INSC. We would have not been anywhere if he was not with us. I do not have words to thank him enough. We all know him. He is a person who gratefully, he basically comes here every year, and his lectures are the ones which, if I could do anything, I would extend them to like 5 hours per lecture or something like that. Anyway, a brief intro. Professor Mohammad Shafique is a professor of computer engineering, New York University, Abu Dhabi, United Arab Emirates. He received his PhD in computer science from Germany, I guess, Karlsruhe, Germany, and has since held prominent academic and research positions, including a full professorship at TU Vienna. He has also made impactful contributions to R&D and innovation in Pakistan, co-founding a technology startup and leading national ICT projects. Professor Shafique's research spans AI, hardware, brain-inspired computing, energy efficient systems, hardware security and embedded systems with applications across Internet of Things, cyber physical systems, and ICT for development. He has authored over 250 publications, 6 books, and holds multiple patents. His work has earned him numerous prestigious honors, including the ACM SIGDA Outstanding New Faculty Award and the AI 2000 Most Influential Scholar Award 3 consecutive years, the Inspire Research Excellence Award, and recognition from Nature Electronics. He was also named to NYU's Faculty Honors List in 2021. He is going to be delivering 4 lectures. 2 of them are in this first session. And the title is basically Advanced Trends in Energy Efficient and Secure Edge AI Systems, Challenges, Applications, and Architectures. Dr. Saab, I welcome you over here. The floor is over to you. Thank you very much indeed.
Thanks for the invitation and also the kind and long introduction. It's always a pleasure to be here, interact with you guys, talk, and hopefully showcase the work. I do have a lot of slides that Dr. Yusuf was mentioning, but I'm not going to torture you for that. I'll try to keep it brief, as much as in overview form. If any one of you would like to go into details, I would be, of course, we are available all the time. So please feel free to dig deeper with me in discussions during our sessions, during the walks. This is the main purpose of the summer school, so that we all are here. We all can interact. I would like to start the work with acknowledgement to also these centers, because most of the work we all know in research is being funded from different sources. NYU has been very gracious and generous to give us quite a lot of resources, as well as the Center of Cybersecurity, Center of Interactive Smart Cities, Center of AI and Robotics, Center of Quantum Technologies. And through all these centers, we have built an excellent team. So last time when I came, I only showcased the work from our evening lab, but over the last 2 years, I have been also establishing another lab, which is Integrated Quantum Autonomous Systems, ICAS, and we have now the first version of this lab setup. We have done first basic experiments on robots in that, and hopefully over the years, we will be expanding this with humanoids and multiple heterogeneous robotic interactions and stuff. The whole goal of my lab, if you want to summarize in one word, and that's the title, is basically enabling energy efficient and secure and safe edge AI, which means that how to put the intelligence across different edge devices in different systems. We all know that autonomous vehicles, any mobile systems now, robots are one of the primary ones. But we do work in the area of healthcare, because since we have established a lot of expertise in core AI, we can also deploy them to solve very interesting problems in smart cities, in healthcare, as well as now in, of course, quantum technologies. We all know that we are in a new age, and now AI is a de facto standard now. Whoever doesn't know anything about machine learning AI is not going to match up in the race. And we always summarize this with this thing that, in the first stage, we were basically talking about the manpower, skill, strength. In the second age, we saw the industrial revolutions. And in the third age, everyone is talking about the data is the fuel and innovation because the new politics. In this politics, we have already seen and across different events in the past 5 years. When we talk about this data, there is one very important thing which is missing here, and I think with the recent sanctions from US in the past 1 year, in different countries, people realize what is that missing piece. Can someone tell me? If data is there, we have AI inference, there's one big point which is missing. Exactly, computing power. If we don't have AI chips, unfortunately, we cannot do anything. Now, in order to have computing power, you actually need the real power, right? The power grids. So if you talk about, if you look at the current landscapes, even the big giants who are doing a lot of machine learning or LLMs, multiple LLMs, they are also like buying these distributed power grids and kind of stuff. So power generation and compute power, these are like two biggest points. So I think the politics which is going towards that is primarily who is getting those AI chips. In general, if NVIDIA is producing those GPUs, who is going to get those GPUs? So if you don't have that kind of compute power, no matter how intellectual you are, can you still compete with this? Unless you have new type of models, and hopefully we will mention some of them, that people are looking into alternate machine learning models. And that's I always, in my talk, I will give you some kind of thought-provoking points that you can later on pick in the debates. I mean, I see many faces like, so you have also seen those slides. Unfortunately, in one year, I cannot have a drastically radically changed slides there. You will see nice. We have a lot of set of applications which are using machine learning. So I'll just skip that because I think we summarized pretty much now everything is coming with the tag of machine learning and AI. Now, what are we using it for? It's primarily we are learning important information from data, deriving predictions, short-term, long-term predictions, and try to use that information now in a new era, which is called agentic AI, is to learn, interact, and again relearn kind of stuff. So I always talk about this thing. I'm a fan of that. So IBM earlier times in the late 90s released something called IBM Autonomous Computing Roadmap. If you would have, or someone would have read that, they already talked about that, how do you go from autonomous to self-aware, self-aware to intelligent, intelligent to cognitive, and cognitive fully basically mean that the systems would be able to learn from the environment, react, and then learn a new piece of knowledge and then contribute to the learning environment. So which basically means that if you can think of the autonomous robots being pervasive with us, they have to kind of react and learn continuously. And that has given birth to a new, completely new domain of continuous learning, and that content learning effectively is now coming up with everything. I mean, many use cases, autonomous driving, lane detection, segmentation. I'll show you some of the examples, done in our lab also. And of course, this is one of the projects that was funded by the Multiple Sclerosis Society in Abu Dhabi, where we are doing advanced deep learning backend pipeline for processing the 3D volumes of MRIs to do some kind of longitudinal analysis that can help the researchers. Similarly, in autonomous vehicles, you might have seen a lot of stuff that are space processing. I'll talk about that. This is completely okay as a first starting point, but when you want to excel in the TRL, technology readiness level, you have to go all the way up to full system prototyping and demonstration in the real world scenarios. And for that, I mean, now I give a note, digital twin has been inevitable technology, and that's why there are a lot of simulators. So we have been working with AutoWare and Carla for the autonomous vehicles now, integrate those kind of stuff. When we look at what are the current trends, I'll talk a little bit about that also. We all know that the generative AI has also proliferated basically everywhere, and people are also talking about tiny generative AI, like tiny LLMs, tiny VLMs kind of stuff, so that your robots can also just run LLM on the fly, even if they don't have kind of big Wi-Fi bandwidth. And we have seen that this has been, for example, classically used with the text generation, but visual generation like Sora now is there. People have now integrated multiple generative AI tools to even create their movies with songs and stuff. But as like I come from the hardware background and system level background, I'm a big fan of these last two blocks, which is code generation and hardware generation. And I think this has significantly increased the productivity of programmers and hardware engineers. Now, if someone says that I am a student and I don't know much of the coding, they don't need to spend much time in the coding also. They need to learn programming. Programming and coding are two different things, Programming is the analytical mindset of that, how you can envision algorithms and stuff. So if you know that what kind of algorithms you are building, it can generate code in Python, C++, whatever language that you want to do. And you need to understand still the language syntax so that you can debug and do that. But now there are many strong debugging tools kind of available also. So I think this thing will really improve significantly over the period of time. I already know, I won't say the name because I just asked his recording, so it's recording. I already know very big companies, they have already deployed large language models, in-house LLMs, closed source, to automatically generate their tools. Now imagine that if you are going to develop a new product, you need like 5 different tools to support that. So if a generative AI can, for example, agent can generate a tool for you, your time to market is significantly shorter. You are much ahead in the competition also. Hardware generation, now imagine that if we don't have the full scale hardware generation ecosystem here, then still generative AI can help me. And I think hopefully if I get some extra time in the last day, it's like tomorrow maybe, I'll give you some of the ideas of the work that we have been working on. And there is a completely new conference which is being created, IC-led, massively financed and supported by Synopsys, Cadence, which are the basic companies for this thing, for how to use large language models to effectively generate the RTL, Verilog, test cases, blah, blah, blah. And so there is a lot of stuff that you will see that. And there are many, many problems there, like the data contamination problems and those kind of stuff that you have to face. So I think that as any abstraction level where engineers or scientists are working, you can use this generative AI to help you. Besides applications, tools, hardware, think about anything, you can basically use that. And I think we can talk a bit more about the philosophical stuff, and that's wherever you are going to generate any kind of pattern or text or learning from any picture or something, you can do this thing. You already know that AI image generation is very advanced. You have also seen the recent features where you can even give a picture and it can even modify the picture. Earlier, the image modification was a bit tricky, but now image modification is also very, very advanced. Auto-regressive models have actually overtaken quite some over the diffusion models. So I think we are in an era where, I don't know, I mean, if we can believe what we see, which basically has given me a motivation to do, again, a research in deepfake detection kind of stuff. So I may show you some of the results for that. So deepfake is a classical kind of, stuff where people were faking, and now the biggest problem for the community is like detection of the AIGC, like AI generated content. So if I cannot delineate between it's a real image versus AI generated image, how would you believe your media? Am I right? And we have seen that in recent political events, people have shown pictures and videos and stuff, and they were completely fake. Later on, they figured out, people figured out that. How do they figure out? There are tools which can do the analysis, spatio-temporal analysis, and then they can identify that. And similarly, like all the video generation is also very, very advanced, and I'll skip just through that. Maybe I should mute myself. Now, when we talk about real-world systems, 80 to 90% of the real-world systems are basically embedded systems. They are deployed everywhere from your watch to high-end robot. And when we talk about the real-world cyber-physical system or any kind of autonomous mobile system or any edge AI system, accuracy is not the only thing that we are concerned with. Accuracy is only one thing that we're concerned with. But a lot of times we trade off the accuracy with a lot of other metrics. And for me, of course, performance is by default. Like if you don't get anything in real time or low latency, a lot of times those applications are useless. But for us, one of the biggest thing is also dependability, security, reliability, those kind of stuff, safety. So if imagine that you have a quad rod which is doing a navigation, and if I say that I can simply hack it, then its purpose is useless because you can just put a bag here, anything can be in a bag, and explosive or any malicious stuff. And then this bag is invisible to the quad rod because I have done an adversarial attack on this thing, and it won't recognize that bag. And when it builds the map, it just sees everything except this bag. So it's a big security threat. Or you can actually make these dogs or autonomous vehicles hallucinate things which are not there in a scene or which are there in a scene and they cannot see that. This is attacks versus hallucination attacks. So security is multifaceted, like making the actual core functionality void, like it just doesn't do the task that you are like thinking it should do. On the other side, you can unleash the IP. For example, I've spent millions of dollars to build a deep learning engine. And what we do is that I can just do a IP stealing attack using side channels, and then we can just IP. This is again bad stuff. And privacy is like another stuff where I can unleash the data which is used for training. And those are all issues which have there. Again, when we talk about practical system, adaptability and interoperability are other things also. We'll talk about that. But the biggest point that catches you there is the power energy envelope of your system. If your system can only operate at, let's say, 10 watts and it has no power beyond that, unfortunately, you cannot have a very high-end security or, 5-layered walls, security walls around that. You cannot have like super powerful GPUs. You cannot have very extensive large models. So how do you get accuracy, security, privacy in an extremely small power budget? This is the real challenge. So a real world problem is actually a multi-objective optimization problem. And if you can formulate this well, you are ahead in the league. I always show this thing that machine learning, like people talk about always aeroplanes violating the CO2 and all stuff, but machine learning is actually consuming much more power. Very, very old study, which was published in Nature Machine Learning, showed that at that time, one of the generative model training actually took 5 times more than the aeroplane. And now the modern ones are like super, super costly. This graph I always put for just so you can get my slides and zoom them. These are the AWS power services, like services power consumption. Where are we heading forward? A slightly old graph, I didn't get time to update that. We all know that we started with regular convolution networks all the way up to transformers was one of the biggest breakthrough because then it led to a lot of generative models. So it's a foundational basic block of any generative model. Of course, there are a lot of other building blocks that people are talking about. If you really see the modern multimodal language models are now talking about state space based model combining with regular generative models also to have much faster and much complex learning. But both have their pros and cons, time series analysis versus a one-shot kind of analysis. And then we are like, we have seen the evolutions in last 2 years rapidly in generative AI. And so where are we going next? I mean, there are many different mindsets. There are many different thoughts that people are talking about. There are many different cases, but I'll talk about where are the investments going, and hopefully you will get that. The ultimate holy grail thing that people want to solve is AIGC, like, I would say that the general purpose AI, or artificial general intelligence, and many different names for that, which can still learn on the fly. Is it like one network? Is it like one model? Or is it a combination of multiple different models? So it's, I think everyone knows now it cannot be a single model. So Jan Lucan has written a very nice perspective article. What are the basic building blocks of a modern AI system? I think I would recommend you to go and read that, and you'll see a lot of like very nice overview of the thoughts of these experts which people are proposing. But like there's a lot of stuff which is being found into this thing. People are talking about brain-inspired computing models, which can be extremely lightweight, less complex, and much higher and better cognitive or learning skills. I think those will also be one of the building blocks already for the systems. Again, I keep coming back to the power and power so that you understand what is our league. GPT-4, not like really an official number. In one of the articles, he mentioned that it is more than 100 million, but how much more? Nobody knows. There are speculations. But of course, things are going forward. It's not like they're doing one-time learning, they're continuously learning. So if there is anything reported, they will continuously update their models and stuff like this. So if you look at this, I mean, the way that we have excelled, it's literally over a couple of years. Earlier we thought, like, I mean, that's when I did my PhD, and I thought that, okay, man, this is excelling at not that fast rate, so it's good, we can catch up with the pace. But with the last 3 years, you can see it's exponential curve now. And why it's exponential curve? Because the return of investment is also very high for these enterprises. So these enterprises can keep on investing. I mean, it's insane numbers. Earlier we talked about someone got like, $10 million. Now that $100 million is like nothing, for the Series A funding. One of my friends, he has a startup. The first seed funding was 36 million. The next one was $250 million. So it's like insane. It's like pennies for them eventually. Valuation goes to $1 billion very rapidly in 1 year or 2 years at most for these companies. But now if you look at the investments they're looking into tens of hundreds of billions of dollars. So I'll talk about one of the image where now it's UAE in general has a strategical agenda about the AI, and they have planned $1.4 trillion in investment in AI in the next 10 years. And the Stargate, everyone knows, maybe it's a $500 billion kind of project, and one of the biggest part will come to Abu Dhabi also. So these are like kind of stuff that we are talking about. So these are now old school. The new numbers are like massives. It has given rise to many different initiatives like Cerebrus producing a wafer scale chip. Wafer scale chip is a landmark. I would say that technologically, whoever works in hardware knows yield is a bigger problem. None of these hardware companies were able to build a chip on a wafer. It's not like they cannot build, it's like they cannot sell that because one chip in one wafer having faults, yield is very big problem. Cerebras was able to do that because the wafer scale chip is actually AI training engine kind of stuff, which means that they have very regularized neural accelerator cores and replicate them. So if you are aware of earlier times MIT Steel project, then you will see that it's basically very similar philosophy. And even if a couple of those neural accelerators are faulty, you can just design very nice tools where you can do the mapping and stuff like for that. I come from energy efficiency background. I always raise a question. A big generative AI tool playing a game with a human, is it fair? And I think Adil will also say that no, am I right? Because the power consumption, look at the power consumption. So we are talking about like tens of gigawatts, hundreds of gigawatts. We are only 12 watts, 20 watts, sorry. So if we are working in a 20 watts kind of stuff, then how we are going to compare with ourselves with them? So anyway, moving forward, investments are ramping up. This is the Stargate initiative, which was just recently released when Trump visited. They also kind of inaugurated the model of the site. I think that these kind of initiatives are extremely important at the national levels because they completely change the mindset of people from school to all the way up to the career levels in the high end also. You exactly know that what is your priority and what are you playing with and what is your playground actually. Until we don't define our playground, that where do we want to win, you are not able to build a strategy properly and you're not able to take bold steps there. And now, I mean, I was just talking to someone and he told me that I think officially this year or next year, AI will be taught even in the primary level, like they will be teaching students how to use machine learning AI so that it comes into their thoughts. And I personally think philosophically it is very important because when kids are growing, they also build their ethical and moral norms, which means that if they are learning these technologies, and we also learned our technology of our time, and not my old time, but like the times that we are still there. The thing is, we exactly know that how the morals are kind of merged with these technological advancements. So whenever I am building anything, my goal is always that I want to build something which can help humanity in both ways, usage versus a human resource training and generation. So if you have good kind of, and this is what Yusuf was starting, that the good aspect of technology. And I think these kind of initiatives define any nation that where they want to go and how they want to teach. And this also, of course, opens a lot of kind of stuff. So this has also led a complete change in the architectures of computing. I started my career with digital signal processors. At that time, this was the most advanced chips by Texas Instruments, Nexperia, Philips, for example. Later on, the age of ASICs came, where I did my PhD, application specific inspection processors. And then afterwards, now multiprocessor system on chip came, and now everything is neural accelerator, neural accelerator, neural accelerator. As you can see is that every big chip is talking about a neural accelerator. Now, of course, system on chip will remain there because neural acceleration is not the only task. You need a lot of other kind of tasks when you have to do any kind of machine learning. So most of these things are coupled with regular RISC-like processors, and that's where RISC-V is actually the now one of the most like properly used or widely used kind of base processor. I call it as a base processor. So the future would eventually be a lot of these heterogeneous accelerators, and it's even present, I would say that, and with a lot of these kind of RISC-like processors, which will be coupled together, and that's your chip. The goal would be that how do you generate those kind of chips very fast? You might have seen that all these companies are very rapidly producing these chips. there is a lot of generative AI in the back end going on, which is helping them to excel very fast. So I think that in future chip generation, and there is a big momentum on democratizing that open source hardware. And I think once the open source hardware initiative will be well established, chip democratization is there, then innovation would be eventually on how the way that we use these technologies. So AI acceleration market is also exponentially going up. So with trends and challenges, you will feel that where we are heading forward. And why I always show this thing, because you need to exactly know the which technology I need to learn now. So if you have seen the machine learning is there and now start with CNNs again, I think it's very old time now. You don't need to waste your time on this thing. Just pick the problem which is important here. And there is a go to Hugging Face, download your model, whatever you want, and then fine tune that. What is the art then? I mean, I can get all these foundation models. I can get all the, like transform models. What is the art? Art is actually the way that you think the problem solving. Like, is how well you can define your problem that you want to solve. What are your system constraints that you actually want to solve? There are hundreds of models. Which model will actually solve my problem? So I can pick 4 of these models, not 40, and then I can test these 4 models, and then I can step by step, build my system out of it. This is how you go forward with that. Security and reliability, I would say that this, like, again, depending on which abstraction level you're working, if you're working at the chip level kind of stuff, then soft errors, variations, aging, these are like traditional problems. They are aggravated every generation. Even the modern generation of chips, like, which fabricate at 2 nanometer, has significant issues with the soft errors. And you don't see them because people put lot of guard bands, dual AI processors, for example, to the lockstep based kind of processing. But in general, these are the things. On the application level, you have adversarial attacks at the inference time, backdoor attacks at the training time, model stealing attacks at, again, the deployment time, and neural trojans again at any time that you can deploy. And these are the hardware trojans, and these are the side channel attacks. Side channel attacks used to steal the IP. They can be also done to many different things. There is a recent generation of attack. It's not in the picture. I will hopefully show in my 3rd lecture tomorrow, which is called phantom attack. And these are like very powerful attacks. I don't need to perturb anything. I don't touch anything in the environment. I'll show that I will project something on the wall, and it can fool your autonomous vehicle or anything. And people have done this attack on real Tesla cars also. They have shown crashes. We will talk about this in tomorrow's lecture in more details. Coming a bit more scientific now. I have used half an hour, am I right? Or less than that even. I'm a bit speeding up so that we can spend time here. So my team works at 3 different abstraction levels: hardware, architectures, and software, across different columns. And you have now already heard that security, efficiency, these are our primary one. Reliability comes from time to time whenever we have industrial project to mitigate that. Otherwise, it's very difficult. Where do you deploy this thing? We did a very large scale industrial project on this thing, and that went into then some industrial tool chain also. Application is like, eventually that gives us that whatever technology that we are building, is it really good, useful or not? That is the point. So in the last 4 years, I've learned whatever we have done in earlier times is good at a certain level. If you want to take it to the next level to the technology and want to showcase it to customers or any potential investors, you need to showcase in the real environment. Interestingly, the real environment deployments unleashes many different new constraints, and I'll show you that also, which basically means that your research actually is much better fueled also. So that's why I started working on full system deployment, but then this requires a bigger team and stuff. We have been working with quantum neural networks, spiking networks, reinforcement learning, multimodal LLMs. I'll show you some of the results for that. We are building up accelerators for those kind of stuff. We are looking into tools to compress those networks using pooling quantization, neural architectural search, and those kind of stuff. We are looking into security problems, using these large language models also for the security detection and stuff. The hottest problems nowadays for these generative AI is hallucination and jailbreaking. So we have been an amazing success recently, just last month, a groundbreaking result in jailbreaking also. I may give you a little bit hint about that also, and things like that. So let's move forward to a bit more scientific stuff. These are just the pictures of my labs. These are like main research lab and this is the engineering lab for the lead systems kind of stuff. And this is the new ICAS driving lab that I have established. This is a scaled down driving track to kind of, emulate the scenarios of driving. This is a full view because you don't see this completely. These are the different quadroves that we have bought and working on. We have a small 3D printing facility here. This is still a very advanced 3D printer, but we have a very large scale core technology platform in NYU Abu Dhabi to print many, many things. What I'm going to do is that I will skip all these introductory slides unless someone asks me. And I want to come to this thing that what is that slide? This slide is just showing that if we are going to get some really good accuracy, we need to go with the bigger models. Now, if I have a model which has billions of parameters, unfortunately, I won't be able to compress it to a very small chip. No matter how powerful this chip is, I have a very tight power budget of sometimes 1 watt, 2 watt, 3 watt, so how will I do that? So if I have to live with these kind of models, I need to go with some techniques. So model compression is always the first thing that everyone does. And now it's again a de facto standard, by the way. 5 years ago, it was a kind of a tool that people were using for need. Now, even if you don't want to deploy it on edge, and if I say that I want to even do a big, large GPU training, I still do quantization. I still do sometimes pruning or some advanced method like speculative decoding for large language models and things like that. And why do I need to do that? Because the training time or the inference time or the service time is very costly. So you know that, if you just get the latest ChatGPT service, it's costly, am I right? So every query will be running on some machines, some GPUs, and they cost power. And if they are costing more power, your service is costly. Now, every query does not need an extremely large model. So you can have small models, medium-sized models, large models. Which query is facilitated with which model, you don't know that. But there are techniques which can predict, speculate, and then take it through small models to all the large models like cascading kind of stuff. And people do those kind of stuff also. But even if you look at this, now quantization is also a de facto standard from my point of view. We don't go into floating point. We directly try to train in a quantized way. And the inference is already running on a 4-bit or 8-bit quantized models. So the state-of-the-art techniques remain pretty much the same in terms of category. Like we do structured pruning. Unstructured pruning is very rarely used in some architectures because they create sparsity. And sparsity is very bad for regularized accelerator architecture. And quantization. So these two are the really big, important things. And then you have these architectures which are very customized, MAC units and programmable MAC units kind of stuff. Pruning, I think some of you already know. Some who don't, I just tell you if this is your weight array. Some of these weights may be just insignificant for me. I don't need zeros. I don't need maybe ones. I don't need maybe twos. So what I can do is that I can do some kind of method. I'll talk about that method in a while. And say that kick out these neurons, these weights, these filters, depending on structured versus unstructured. And this is an unstructured one, so which means it creates a sparse representation. In structured one, I can kick out this neuron. I can kick out maybe filters of this neuron if this is a multi-channel kind of stuff. And you can simply have a reduced complexity of this kind of thing. So there are many different methods, class distribution, class uniform, class blind. I just skip through those. This is a iterative pruning methodology. Typically, pruning is done in an iterative fashion. Single shot pruning is okay for very small problems. For large problems, very complicated. What we typically do is that if you are given with a network, you start with, let's say, the back of the network and starts computing saliency of different neurons. And the idea of saliency is primarily that how important this neuron is for the final output. So there is a metric called conductance. You compute the conductance of every neuron. And then based on that, you will then just simply can filter out. People have done different metrics like L1 norm, L2 norm, and things like this to compute conductance. Effectively, when we kick out those neurons, let's say I have to remove 10% neurons, so 10% most insignificant neurons are kicked out. Then we do a little bit of fine training to recover the accuracy. And now you can do the second round of the pruning until you have reached your accuracy constraint. And if you have also constraint of size of a neuron, which can, the model which can fit into chip, then it has to go on. Otherwise, you have to come with a different architecture. The problem with this is that there is still a bottleneck at some point in time. For example, you have two constraints that I want to have this accuracy and my model size should not be more than that. What if there is no optimal solution possible for the initial pre-trained model that you started with? What would be the way that you will do that? Can someone answer me? If I cannot prune it to fulfill my accuracy or change the starting point. And how do we change the starting point? You have to learn or train a new network, am I right? So, sorry? Very good. So we actually can start with a neural architecture such, and that's where the NAS actually get in. So hardware-aware NAS is actually where people give these constraints right at the start. And then, of course, it's a super complex problem because it's a computationally explosive design space that your optimization algorithm has to solve and explore. And it can explore those design points which a manual designer would have not done during the architecture building. So NAS is now again is like really everywhere in those systems. So just to give you an idea that pruning does not kill you so much, this is a LeanNet. I can show you other results also. Pruning with a little bit of fine tuning, you can kick out 90% of the neurons, and don't do that in VGG. If you don't fine train, you can recover to 60% accuracy. If you do a 1 to 2 epoch fine training, then you can actually get up to 97% by accuracy, which is okay. The last neurons you cannot kill because then those are the sensitive neurons which are actually learning the features. Quantization, this is a very simple one. We have much more advanced quantization results. Up to 8-bit, people have seen there is not much difference. This is typically done post-training quantization, PTQ, which basically means you don't need to retrain that. You just, whatever you have trained, just cut it to the 8-bit and then your network will still work perfectly. Actually, sometimes it gives you better results. And it gives you better results because of the regularization effects also. Because your models are nowadays, or every model is overfitted model. We have been doing gradually, slowly, some research in architectures, accelerators. So we have built a neural accelerator. We have compared it with different accelerators and we have shown good results. Systolic arrays, I mean, this is a slide that I always tell you so that you know that how does it work. You have pretty much systolic array-like architectures. Of course, there are now advanced architectures that have more advanced control features. The PE is primarily a MAC unit with some registers. One register will get your partial sum, one will get your weight and input data. What we do is, this is called a weight stationary mapping, which means these are the filters that we have mapped, first, second, third, fourth. And what we do is that we just feed the input in a pipeline fashion to that. And cycle by cycle, this data is flowing through this pipeline. This sum, partial sum will come out to this register and then added up there. So we are getting basically the sum of products at the end of this thing. And then later on, you will have the other blocks which are doing the kind of, next steps of your thing. For example, you can still do the dropout kind of effect and things like that. Having said that, let's move forward. So this is MPNA, which is the massively parallel neural architecture. We have the main 2 compute arrays for different type of stuff. We have accumulation blocks, we have coding activation layer. And the biggest problem is the control unit, which is the main IP, because this control units make sure that you are able to reuse these partial sums as much as possible and go forward that. Capsule networks architectures, I kick out this thing because this is obsolete now. One of the recent work that we have done is the Swiftron, which is a transformer, one of the earlier ones, transformer accelerators, which also got into news. We build massively parallel transformer architectures. Now we are taking things forward using generative AI, that how we can build up these architectures in using large language models, then they are scalable, because we know that our algorithms are rapidly scaling. So I want to scale up my customized algorithms also. So you can see that, this is like a, the multi-headed attention block, and this is the regular attention block, and then these are the normalization layers. And we have mapped it on multiple devices, also different Xilinx stuff, and we have also synthesized it using this. One benefit of working with these centers is that we do get the proper hardware engineers who can actually build chips, and then we fabricate those chips with the global foundries or other kind of partners. And my colleagues, for example, in CCS, who are working in precise logic logging kind of technologies, they have been building chips also a lot in these things. If some of you working with hardware, you already know that computing is only one part. Computing may be 20% of your energy consumption. That 20% is still very important. You can reduce computation. So one benefit of pooling is that I don't only, and quantum, of course, I don't only cut down computing, I actually cut down the memory requirements also. And memory is the one which consumes 60% to 80%, depending upon your data flow, of the total energy of your processing. So, which basically means that we have to do something for the memory. And if you are a computer architect and you are looking into the current trends, you also know that every chip having a big challenge with the memory. And of course, memory technologies are very mature, so people are still able to play a lot of stuff. What you need memory for? You need memory for activation buffers, input feature map buffers, output feature map buffers, wait buffers, off-chip memories. These are all on-chip memories and off-chip memories. How do you manage this thing? So you need to look into the some kind of still reuse kind of stuff. So one thing is called tiling. This is not like the tiling of the hardware. These are the tiling of the data. What we do is that we tile this data and then map it on different blocks in the memory and do that. So I just gave you some summary of the methods and we can go details later on. For example, how do you identify the reuse? We have developed a tool which can take CNN transformers. It can calculate different level of reuse at different layers. And then we can exploit the reuse to map properly the data on the SRAM memories. We have built data mapping tool for DRAMs. We tested it on the practical DRAMs also. We have tested it on the bank level DRAMs, which have bank arrays and sub-arrays kind of stuff. This is a self-like architecture, like sub-array level parallelism kind of architecture. We have tested on the real bank architectures also. So there is a big research which is going on in this direction, that how do you efficiently place your data in the actual DRAMs, and then from there you shuttle the data back and forth to your SRAMs. And of course, we have shown significant improvements in terms of energy consumption and reductions. I just skip through all these things again. Approximate computing is very attractive. It's very tricky. You need to be very careful where do you deploy that, because it loses some of your accuracy. So if you apply it very bad, then it can lead to significant degradation. If you apply very wisely, it can give you basically free savings. So we have been looking into approximate computing for almost 10 years now, more than 10 years. And we have significant progress and kind of leadership across the globe in this thing. One of the leading ones is Purdue's group, second is ours, third one is in San Diego, we used to go in Brno and those kind of places. Approximate computing, I always give this example. If you look at Lina's picture, this is the original one with the full accuracy filter, and this is the one with the inaccurate filter. Except this, which is a full truncation, all these are acceptable. You won't be able to see much of the difference in that. This is just one very motivational example. The power reduction is almost 92%, but we have built approximations across the different layers. Like we have built open source libraries of approximate address and multipliers, which have been downloaded numerous times, used across the globe by different groups. We have built approximate accelerators. This has been also a great work, which has been deployed into approximating different layers of different neural networks, such that you don't kill the accuracy of the final stuff. And we have also deployed some self-healing kind of approximations where we can actually recover from the errors which we introduce. Again, deploying it on machine learning is a bit tricky because you need to understand the resilience of different neurons and different layers. So we have coupled our studies that we use typically for quantization together with the typical type of approximations, and we have significant results. I'll skip through that. These are the results that can show you that pruning gives you something, quantization gives you something, and hardware approximation gives you some additional stuff. Altogether, you can get quite a lot of interesting things. The big challenge with the hardware approximation is that the time space is very big, because you can approximate any kind of multiplier in kind of like hundreds of thousands of ways. So if you can quantify, you have to figure out that which of these bits will be approximable, what kind of approximate technique should I deploy, which type of adder tree should I put. Are we going to approximate the 2 by 2 multipliers? Are we going to approximate the adder tree? Are we going to approximate the other blocks in the Mac unit, things like that. So the self-healing ones, we have shown that, and this is basically one of this work was done in collaboration with one of the Dutch universities, which went into actually satellite signal processing. And we have showcased that for very tight accuracy constraints, we actually can approximate significantly to reduce the power consumption. And if you are aware of those kilometer by kilometer satellite arrays, then they are very much restricted by the power consumption, and we are basically looking into those kind of problems. I stopped that work. I moved all towards AI. So we'll just give you a little bit of the closing ones towards hardware and NAS. NAS is in general a problem of neural architecture. In layman's terms, I always explain it like this. Imagine I am a tool. Someone tells me that, Shafique, I have a mobile phone. Can you generate a neural network that can fit into this mobile phone, can do a facial recognition in 1 watt power budget? And I want to have an accuracy of 95%. You press a button, you get your neural network out. And this is amazing. So people are using neural networks to generate neural networks effectively. So there are multiple challenges in that. You need to first define what are your basic building blocks. Lot of work has been done on generating classifiers. We have recently some very new work on automatically generating detectors, like the detection algorithms, detection neural networks based on that. There are different steps in this thing. First step is like, what are your basic building blocks? You have a transformer block, you have a convolutional block, you have a residual block, you have a detector block, and things like that. You have a skip blocks. And then you have a candidate generation algorithm, which means that it takes these basic building blocks and generates permutations. It can generate you, let's say, 100 million different configurations, and now pick one. So what is the biggest problem in this? 100 million neural network configurations. Which one of this is the optimal one? You need to search. Am I right? No, searching we are doing. So generation and searching, so it's a genetic algorithm based kind of stuff. What is the biggest challenge? That I cannot run 100,000, let's say 100 million neural architectures on the mobile phone and then see which one is good. Am I right? So what do we need? So all the system engineers know that you need analytical models, which means that I need to build analytical models to estimate accuracy, to estimate performance, to estimate energy consumption. And those analytical models are extremely complex to build. So we recently have a paper coming up at DAC this year, which is the top tier conference in design automation and stuff. Where we have built the analytical models, these are like surrogate models for embedded GPUs, for multiprocessor system on chip. And now by having those kind of energy models, the typical models which were used by, let's say, Songan at MIT was table-based models. This is the first thing that everyone does. A lookup table-based model, which is very simple, regressive model kind of stuff to give you that. But now we have built a proper learned models, through using machine learning. But we have to generate a lot of data for every architecture to first build this model. So by doing this thing, we are able to now annotate these NAS frameworks much better, which means that we can give you much better configuration, which will suffice your, let's say, this whole area is called AutoML, which basically means that how you can automatically generate your neural networks. And you can imagine that if you have a tool which can automatically generate your neural network, you are very happy to do so. Again, more design metrics to introduce, more complex is this NAS framework. We have also introduced some kind of security metrics inside that, so that whatever network you get is not only energy efficient, but also a bit more secure, but then it's thing. So that's it for the first part. I would like to thank, of course, my core team, a lot of students who have been working on this thing, a lot of students who have done these works and then graduated and are at very good places. And thanks. And now I'm open to your questions now. So we have a lot of time actually for questions. I speed up a lot. I still have 10 minutes for question. Yes, go ahead, Siya.
Propose different approaches for parallelism that are doing well. But why are we not going at the core? For example, why not change the architecture from one human to other? For example, LIM, CIM, etc.
Yeah. So, very good question, actually. And people are thinking in that direction. Clarifications, energy consumptions, of course, 80% can be 60% based on architectures. This is clear. Techniques, why people are doing this thing? Because DRAM is a very well-established technology. If I want to build a system today, I can just go ahead and buy that. You all know this thing. SRAM is very regularized. You know this thing. Now, there are technologies like memoristic technologies, people are working into this thing. There are big groups doing in this thing. So my friends like Jiren Chen and Helen at Duke, they have one of the leading groups. Kaushik Rai at Purdue has one of the leading groups in memory computing. We do have some small work in this direction also. It is just not mature at the moment, but this would be one of the futuristic stuff that people will go. The reason is very simple because, instead of bringing memory to compute, you can actually just directly go compute it. There are some baby steps in that already. There is a technology called processing near memory. Samsung already has a chip where they are doing some small processing inside the DRAM chips. Onur Mutlu at ETH Zurich has a lot of work building up those DRAM technologies together with his industrial partners, where they can do part of these, especially for graph neural networks. This is very good. That some of the basic operations that you can do just near the things. Going full, you still need to mature the technology. If I want to go into a fully memoristic, I need a multi-level, let's say, MRAM cells, and multi-level MRAM cells still has a lot of error issues, read instability and those kind of stuff. Sorry? Sorry, I did not. Christian is one of the expert in DRAMs, actually. Yeah. He's because he came from Infineon. Christian is doing his Matthias Jung is doing. They're all from Norbert Wiener's group. They're doing a lot of work. Yeah.
Assalamualaikum, sir. Thank you so much. Regarding you told us about model compression, pruning, and stuff like that. How you balance the accuracy while deciding that, it's okay, I'm pruning the model. So it's how you balance the accuracy, because you told accuracy is not the problem, only one problem. But being as a AI developer, accuracy is also a problem for me.
Yeah.
So while maintaining balance these two trade-off, how you going for that?
So trade-off, when we talk about trade-off, like if you say that, can I get a portion like, $1,000? No, am I right? So if you want to have a Porsche, you need to have $150,000, and then at least for the basic version, and then go ahead from that. So accuracy is like this. If you want to have a Porsche 911, you need to invest money. Am I right? So if you want to have, let's say, 99.9% accuracy, you need to invest compute power, you need to invest resources, you need to have bigger models, bigger chips and stuff. Now imagine that if I have a facial recognition system deployed in a camera and I am doing a near sensor processing there, which means I want to have an AGI chip there, you are doing a temporal processing. Like for every person, you don't do one frame, you do like 30 frames. So you can say that out of 30 frames, if 25 frames tell me it's Shafique, 5 don't tell me, I do a majority voting, I tell it's Shafique, am I right? So the final system implementation, how do you implement this accuracy is different. Now this brings me to the point, what is my affordable accuracy? Am I right? So for every system, this comes in the system specification. When we design a system, specification says, I want to have 90% accuracy, 95% accuracy. Let's take 90% accuracy is my constraint, okay? If I am fine that my system will run very well at 90% accuracy of face detection, then I can take a network which has a base accuracy 99%. I can compress to a level where it gives me 91, 92%. 90% is too at the threshold. 92% is fine. I use this system. Am I right? So this trade-off is like I compress the model, check my accuracy. Accuracy is bad. I do a little bit of fine-tuning or retraining, recover my accuracy. We all know that with the retraining, the accuracy will be recovered. Then check, again compress, check, compress, and then I will find a termination point of the model compression algorithm. And if I get a solution, then I'm fine. If I don't get a solution, I have to adopt a different methodology to do that. Does it answer your question? But accuracy, I'm not saying is not matter. It matters, but you need to define what is my affordable accuracy.
Dr. Shafique, one quick question. For example, if you have
You have to talk a
definite-
bit louder, right?
there is a problem of memory, definitely. And we have different kinds of memories, and then we have to have a data path in between. Now, you can solve a problem to a certain extent with having high performance, high bandwidth memory units in devices like Versal and all that. But what about the data path? There is a serious source of hindrance. Where do we stand in that respect in the world right now?
Yeah. So HBM does the bandwidth problem. Okay. I'm not talking about the bandwidth problem. I think bandwidth problem has been solved significantly to a large extent. We talk about the memory energy problem. Even if I have a very high bandwidth, do I really need to shuttle that data to my chip? That's the problem. That will deplete my battery very quickly. Imagine you have a robot, and robot runs on battery, and the budgeting motors take a lot of memory. Your compute power budget, let's say, is only that, for example, I told this 10 watt. In 10 watt, you have to do all the intelligence. If out of 10 watt, 8 watt is gone in memory, what will I do? Am I right? So power and energy. I didn't talk about the peak power and stuff. Those are all other issues, like how much power I can actually drain. That's another issue, but I didn't talk about that. So we have to cut down the memory energy. Bandwidth we still have. Data path, that's where I told you that data path, what I told you, showed this thing. It's nothing without this controller. Yeah. So what you need is a memory hierarchy from DRAM, placement in DRAM, to SRAM, placement in SRAM, to the way I do. Now, the data path actually is designed based on your data flows that you want to support. If you want to support a weight stationary model, you have a different type of connection. If you want to do input stationary model, you need a different type of connections for that. So the shuttling of data will be completely different. So depending upon your actual data flow graph, your data path structure, your controller will actually control that.
Yes, of course, and it will be a
But data path, of course, design with the memory is important, because I will design my data path considering what is my memory network.
Of course.
So the memory comes first from my point of view. Of course, it's an actual problem. Yeah, no, go ahead.
One quick question.
Yeah.
Take that, Rick.
Yes, thank you very much for the talk. You said something about quantization effect and its accuracy, and sometimes you see regularization even when you have lower quantization. So I was wondering, are there any studies regarding these large language models, and how do they scale with quantization, and what effects on accuracy?
There's a lot of work. Look at Vikas Chandra's work. He was earlier at ARM. Later on, he moved to EI Meta Labs, the Meta AI Labs, and he has been doing a lot of work in quantization of large language models. In general, there is a plenty of work. I think there are 2 or 3. You can drop me an email. I'll show you. There are 2 or 3 very good surveys which summarize this thing. If you want to read the latest work, Vikas recently had a very nice paper on how to do a hybrid quantization for LLMs. Of course, different layers in LLMs have different priorities. The earlier one are learning the coarser structures. The later one are learning the actual context. So depending upon which layer is important for which application, you will quantize accordingly. There are very interesting study for this. At the moment, there is, as far as you know, quantization is mandatory nowadays. The cost is very big. And you might also see this trend with the NVIDIA's architectures. NVIDIA's tensor cores are supporting 16-bit, 8-bit, and now even 4-bit is coming up, which means that there is a need for that kind of stuff.
Thank you very much, Dr. Shafique. In fact, I know we have a lot of questions. We can go on for hours like that, but we have to go to the next topic, and then if it is so, give it, Dr. Shafique. So the next talk is on AI for autonomous systems in healthcare. Thank you, Dr. Shafique.
In the meantime, when I'm taking my water, can someone tell me what is embodied AI? Did anybody hear about? I think people working with robotics should have. What is embodied AI? Very good. Very good. embed an AI in a system interacting with the physical world. So, and the biggest application is mobile systems. Terminologies, earlier robotics was the hot, cool word. Everything now people call about mobile agents because agent is the new cool word that people are talking about. Most of this work is done at CARE and CCS, so I'll acknowledge them.